with PG equals 3, K squared equals 3, and Q equals 0, and I'm assuming that Ks has P as the transversal base point. And I discovered that if I take C in CS, a general guy, and calculate R, C, Ks restricted to C, that I get a ring which is K of x1, x2, y, and z with two relations. One relation saying that x1 times y equals x2 cubed, and one relation saying that z squared equals, y cubed plus a4 x1, x2, y plus b6 x1, x2. So if I look at R of S, Ks itself, that maps surjectively to this map. So this surjective is because Q equals 0. So we can't, if we don't have this, then things would be much, much more complicated, right? And the kernel is our principal ideal. And so let me write it x1, x naught. So I can take x naught in here. This is the equation of S, the equation of C. Right. Now I'm not going to go into this here, but it's a general principle of commutative algebra that I'm dividing here by a regular sequence. The element x naught is a regular element, and so the kernel here is isomorphic to the original ring. And then if you know generators and relations to this quotient, then you can extend them to generators and relations of this, and also with syzygies and with modules and so on and so forth. So I'm not going to say what it means in general, but let me just say what it means in this case. It means in this case that this is K of x naught, x1, x2, y, z, divided out by equations, which I can assume are x1, y equals x2 squared plus a multiple of x naught, something, right? And then z squared equals y cubed plus a4 of, and I can put x naught there in there as well, right? Plus b6, x naught, x1, x2. With the only condition that if I throw away x naught, I get back to the original guys. So if I throw away x naught here. So just for simplicity, so that I don't have to keep writing out complicated equations, let me just write x naught cubed here. This is just for a notation, to keep the notation simple. It's not of any importance. And so, this surface is contained in weighted projective space 1, 1, 1, 2, 3. And it's given by these equations. And that means that if I take this line, P of 2, 3, given by x1, x naught equals x1 equals x1 equals x2 equals 0, then this equation is satisfied identically. So this is this funny weighted line. Of course, as a scheme, it's just isomorphic to P1. And then this equation here, all of these terms vanish, and so this is just the single point, z squared equals y cubed. So the single point. Right? And this means that when I do S maps to P2, by x0, x1, x2, that the morphism is not defined at this point. So if I'm standing at this point, then the map is 0, 0, 0. Right, so Ks has P as base point. Right, and so, the curve C is just inside there, is just given by x0 equals 0. And, the equations here are a bit more complicated. There are a few more terms in the equations, but basically this is just a regular section of something. Right? And so if you understand, in this case, if you understand C completely, you can understand S completely. Okay? So this was in algebra. So in geometry, I've got this map S not well defined to P2, and what I want to do is do S twiddles here and map to P2. So this is the blow up to resolve indeterminacies. Right, and so there's a line L here which lies over P. This is a single blow up. It's a single blow up because I assumed that I have transversal base point. Right, and then this map is 2 to 1. And so you can describe the branch locus. And so in geometry, so this is Horikawa's point of view, or it's of course also the Enriquez and the old Italians' point of view. Right, so it's basically an easy thing, although I'm not. To do it properly would probably take a bit more time. And so what happens is this. There's a line here, L, which is the image of L. Okay, let me write L. So this is in P2. And this is just, this transversal base point. So, here are the, as I said, the two of these things here form a, so I restrict to x0 and I saw the curve. So this is the line with coordinates x0, x2. This is, I think, sorry, I ought to be a bit more careful. Anyway, it's a line in P2. So this is the image of the line L. Right? So if I take any general, this is general line of P2. So this is the image of this curve C. So when I did the first analysis here, I said let's take the curve, let's take the canonical system, restrict it to C. I'm getting a fixed point P and then a G1, 2. And so the fixed point maps to this point, and then there are nine other ramification points. Right? And then you can study a little bit more and understand what happens to the curves. So, there's a linear system here of curves. So two of them base the maximal ideal there, and then one of them is more singular than that. Right? And if you can, this is not especially difficult analysis. I'm not doing it. What happens is this. So the ramification locus is L plus R0, where L is a line and R0 is a curve of degree 9 with a triple point on x1 on L. And you know, upstairs on the S twiddles here, if I take lines passing through there, what happens is there's an elliptic curve here, a minus elliptic curve. I'm describing this. I'm not proving what I say. This is an elliptic curve on S, and it's passing through the point P, and it's blown up to a -2 curve on S twiddles. So it's a -1 elliptic curve on S. It's a -2 curve, a -2 elliptic curve on S twiddles, and then it's contracted to a point by this map. So the map stops being finite. It stops being a morphism, but even after you've made it in a morphism, it stops being finite. Right? So you know, just in terms of local coordinates here, I'm drawing it as 4 separate tangent directions, and that's more or less the same thing as this x0 cubed plus x2 cubed. So this is more or less x0 cubed plus x2 cubed. I'm oversimplifying, of course, but right. And so locally I've got y squared. So locally I've got sort of zeta squared equals equation of L times x0 cubed plus x2 cubed at this point Q. Right, and then you know you can this constructs the canonical image of a surface S with the required invariance. Right. So you know, I don't. You know, there's no kind of. You know, you can do this by geometry, or you can do it by algebra, and you know, the two methods are both you know, equally good. There's no kind of disagreement between the two methods. You know, but this involves singularity theory and sort of rather special kind of geometry, predicting this -2 elliptic curves. You know, it's not especially difficult. But, so I want to say that this geometry is all contained in the algebra. Right? So namely, because I've got this S contained in P 1, 1, 2, 3 with these equations, 2 equations written here. So what happens if I try to map this to P2 by the one canonical map? So this is phi of Ks. So phi of Ks is these x0, x1, x2. So this is the map x0, x1, x2. So, you know, basically it means what happens if you eliminate y from these equations. So at the same time we're going to eliminate a little bit of z from the equations. We're going to leave z. So this y here, exactly as in the treatment of hyperelliptic curves, there was this element y, and the x and the y were invariant under the hyperelliptic involution, and the z was negative under the hyperelliptic involution, -1. Right? And so this y here is really just a rational function of the x's. Right? The y here is just this guy here. So, you know, the main thing that's happening here is eliminate y. Right? And at the same time we're going to eliminate z and replace replaced by x0 squared times z. Right? But anyway, let's not worry about the z for the moment. Eliminate y. So in other words, write y is equal to x0 cubed plus x2 cubed divided by x1. Right? So this line x1 is special. Right? This line is, so this is the, I think this is x1 equals 0 actually. Okay, in which case this equation is wrong. Let me not worry too much about it. Right, and so I do this. So this is a birational expression here. This is a rational expression. Y is quadratic, but it's got a denominator. So now the birational equation for x squared, for z squared, so z squared becomes z squared is, so I'm supposed to write down y cubed. So this is x0 cubed plus x2 cubed divided by x1 cubed times, right, plus a4 x0, x1, x2 times the same thing, x0, x3. Right, and you know, this is not as it stands a polynomial equation. So what I have to do is I'm going to multiply by x1 to the fourth here. Right, and then there's going to be an x1 in there, and then there's going to be x1 cubed here and x1 to the fourth here. Right, and so this means, so let me write zeta to be x1 squared z. Right, so you know at the end of this there is a ring here, which is a 2 to 1 cover here, and the ring is given by k of x0, x1, x2, and zeta. Right, and the zeta is x1 squared times z. Right, and the equation it satisfies, z squared, is this thing here. Right, so this is zeta is x1 times this expression here, which I think I probably got wrong. Anyway, it's x1 times r naught. Right, and r naught is just whatever's left. So r naught has triple points at on line x0, x2 of degree this one cubed or something, I don't know. Okay, so in other words, we can sort of imagine doing all of this in geometry. I mean, or we can read Horikawa's paper, and it's all correct there, of course. Right? But alternatively, we can say, well, I've got this double covering, and so in algebra there must be something here which is a finite double cover of P2, and it's obtained by, we eliminate y, and then we take only the guys over P2 that are integral over P2. Right? So we don't write down z itself, and we don't write down x1 z, we only write down x1 squared z. Right? And then it satisfies this equation. Right? And you can see the so you know, here if I all of this is divisible by x1. Right? So this line was the line, this is the line x1 equals 0. And then if I look at it on the line x1, if I take out this factor r naught, I'll find that this thing again has a triple point when x1 is 0. I'm sorry, it has a triple point when one of these x0s is 0. I'm not sure. What should I be saying? Anyway, this is if I take this expression here, I divide out by x1, I'm getting this term cubed. So I'm getting something quite special. Maybe I'm making a mess of this. It's not very important. So in other words, the algebra contains, even if I've said it in a not very convincing way, the algebra contains the geometry. And you know, of course, you can also reconstruct the algebra from the geometry if you care about it. So you know, this is a kind of ideal situation. This is a situation in which, yes, I should say. So in this case, I've got S special is the guy with x1, x0, x2, x0, x1, x2, y, and z, and two equations. And then I can deform this just by the simple trick of saying x1, y equals this x0, x cubed, whatever it is, plus z, so plus lambda z, deform with parameter lambda, right? And again, exactly as before, the s with the base point. So this is you know, when lambda is 0, goes to s with lambda not equal to 0, with ks free. And so you know, this is an ideal situation. We have a hyperelliptic, at the level of the curve, I have the curve C, and on it P plus G12, with the P of Weierstrass point, and then I can deform this out to, this is lambda equals 0, C lambda not equal to 0, to a G1, to a free G13. Right? And I can do this, everything here is the C and the C, the S and the S remain non-singular. You know, the relation between the rings when lambda is not 0 and when lambda is 0 remains exactly the same. So this is a kind of perfect situation. You can understand the degeneration. You can understand you know, the special case here where the canonical system has a base point, and the general case. You can understand them in a family. So you know, this is of course not the typical case. The typical situation is much harder, and as soon as I get into more substantial examples, I'll come. So the two so there are two other Horikawa cases. Done by the same method. And now PG equals 3, k squared equals 4, and PG equals 4, k squared equals 5. Right. And then of course there are lots of other cases of constructions of algebraic surfaces. When I say there are lots of others, what I mean is there are 4 or 5 others that you can do successfully by these methods. But of course these get much harder. It gets harder. So in particular, these involve codimension 4 rings, the degenerate cases. Or you know, the other cases involve codimension 4 rings with 9 equations and 16 syzygies. So you know, if I try to do all the calculations here, I'll you know, get in a mess. Let me do one straightforward calculation. So let's say what happens when PG equals 4k squared equals 5. So Horikawa called these numerical quintics. So meaning that they look, you know, they have the same numerical invariance, q equals 0. They have the same numerical invariance as S5 in P4. Sorry, S5 in P3, non-singular. Right, and so you know, let's consider this. So we look at the linear system Ks. Then you can show that either if this is free, if Ks is free, it defines a morphism. So the morphism is taking phi from S to S bar in P3, and this is still a quintic, right? So this, you know, the degree of the map, the degree of phi times the degree of the image is equal to 5, and 5 is a prime number, and so the only solution to this equation is this is 1 and this is 5. Right, and then you know, this contracts. This is the canonical model. So in this case, you know, in this case, if you look at the 2 canonical model, then I get 10. The 2. If I look at H0 of 2ks and 3ks and 4ks, then this contains, you know, 10, 15, or whatever it is, 20, 21 sections pulled back from P3. And when I go to the next one up, 5k, so it contains however many is 8 choose 3. 8 times 7 times 6 is, yeah. What have I said? What have I said here? This is 10, this is 10, this is 10 choose 2. Sorry. This is 5 choose 2. This is supposed to be 6 choose 3. 6. Sorry, this is 20. And this is got to be 35. And this is so there are 56 monomials, right? But with one relation. And therefore the sections coming from P3 already give me the complete canonical linear systems, pluricanonical linear systems in each of these degrees, right? And you know, the 5k is very ample, so there's no more. The ring is just this is the whole canonical ring of S. Okay, so what are the alternatives? So if Ks is not free, there's a little argument that I'm not going to worry too much about, saying that it has a unique transversal base point. Right, so that means there's a point P in S, and all the curves C, every curve C in Ks, the curve C passes through P, and most of them are non-singular there and meet transversely. Right? So exactly as before, the word transverse here means that the equations of the curve C generate the maximal ideal. Okay, and so what happens is that so again you can argue geometrically or so the thing that happens here is that we look at this map phi ks from S to some surface S bar in P3. Right, and now it's definitely not defined at this point, and so I have to do S twiddles. Right, and now if I take the linear, the mobile, the free linear system, so call F the blow up there, F upper star of Ks minus the exceptional curve line, exceptional curve of the blow up L. Right, then this linear system, so I call it D for example, D twiddles. Then D twiddles is free, and of degree D twiddles squared is 4. Right, so I had this Ks squared was 5 here. After I pull it back and subtract off one copy of L here, I'm left with 4. Right, and so therefore this map here, this is phi D twiddles. I've got a linear system on S twiddles. I'm taking the map to projective space defined by this linear system. I have degree of the map phi twiddles times degree of the image is equal to 4. Right, and how many solutions does this have? Well, it's if the map were birational, then the image would have to be a quartic. But a quartic can't be a surface of general type, so that's impossible. So the only actually possible solution is 2 times 2. And this means that S bar is a quadric in P3. So it's either isomorphic to P1 cross P1 in its Veronese embedding, or it's a cone right, and this S twiddles to S bar is 2 to 1. So exactly as in this case, exactly as in the case I'm just rubbing off, you can say exactly what the branch locus has to be. So in the case, so Horikawa calls, so this is type 1. Right. And this is called type 2 sub 1. And this one here is called type 2 sub 2. And all of these cases really happen. So in 2-1, I've got P1 cross P1, and the branch curve is of by degree 6, 8. So it looks like, so let me draw the P1 cross P1 like this. Right, so it's got, on each of these fibers it has degree 6. So there's an R0 here. So the branch locus, the branch curve is R0 plus a line. So the R0 is in 6, 7, and the line is in 0, 1. Right, and then the linear, the R0 has a triple point on L. So you know, perhaps it's not surprising that you can make this construction, because if I could take I take P1 cross P1, I draw on it a curve of degree 6, 8, and then I take a double cover, and then I ask, who is that in the classification of surfaces? So because I've taken this 6, 8, the branch, the genus is, corresponds to so if I had R in 6, 8 non-singular, and then S to P1 cross P1 branched in 8 in this R, then KS would be pi upper star of H1 plus 2H2. And so you can calculate its dimension. Its dimension will be 2 times 3, so H naught of this is equal to 6. And you can also calculate its Ks squared. And that's 8. Hey, maybe I've got something slightly wrong here. So, you know, when I pull out this curve here, when I pull out this singularity, it decreases the genus by 1. So I don't know why I've got 5 here, not 4. And then I have to contract a minus 1 curve, which decreases the k squared by 1 more. So the k squared goes right. I'm not quite sure why I'm getting 6 here. Anyway, let me not worry too much about it, because I'm going to do this more algebraically. So, you know, there's a... Maybe I should have... Maybe I'm lying. I'm sorry, I think I'm lying. Anyway, there is a geometric description of the branch locus. I don't know if it's something like that. Let me not worry too much about this. I want to do this by algebra. Right, and then in type 2 there's a similar description, except that the surface is not P1 cross P1, the surface is the scroll F2. So similar description of S of type 2 over the scroll F2. Right? And so, you know, if you just want to construct the individual surfaces, then, you know, there's nothing to stop you doing it. Just do it. So look, let me just give an impressionistic picture of the branch locus. Right? It has 2 infinitely near triple points. So each of these decreases k squared by 1 and decreases pg by 1, and then at the end of it there's a minus 1 curve that has to be contracted. That decreases the k squared by 1 more. I think. So I want to do this using these algebraic techniques. And so I'm going to do the same thing as I did in the easier case. I'm going to take Ks. I'm going to take a general curve C in it. And then I'm going to take Ks restricted to C. Yes? So, you know, Ks times C is 5, and so Ks times C restricted to C is a fixed point P, which I'm assuming, and then plus a G24. Right? So so this means that H naught of C and Ks restricted to C is 3. So this is C is given by x naught equals 0. Right, so I had 4 on S. Now I've just set one of them equals 0. I get 3, and then I had 5, and here is, so I have a linear system of degree 4 moving in a projective space of dimension. And this, the only way of doing this is P plus 2 times G12. Okay, so this is Clifford's theorem on the curve C. So C is a non-singular curve, right? It's non-singular at P because I told you that I have a unique transverse base point. So there's a non-singular curve in that linear system, and it's non-singular outside the point P by Bertini's theorem, if you like. Right, and the genus of C, how are we going to calculate the genus of C? Well, we're going to do the same thing as before. Ks plus C times C, and this is 2Ks times C, is genus, so 2KSC is 10, and this is 2G minus 2. So genus is 6. Right, and P is a Weierstrass point. For exactly the same reason as before. So this curve has got a G12, and therefore it's a hyperelliptic curve. Therefore Kc is 5 times the G12. Right. On the other hand, it's Kc is also equal to 2Ks restricted to C, and this is 2P plus 4 times the G12. So if I set these two guys equal, then I get that 2P is in the G12. So it's P is a Weierstrass point. So now, so C is a curve of genus 6, and P in C with 2P is a G12. Right, so I can write down the ring of R and C and P. And this is equal to, so we already know this, I did this construction earlier today, this is X, Y, and Z. Right, where this has got degree 1, 2, and 2G plus 1. So earlier I had this number 9 that was very nice. Now I've got this number 13, which is very strange. Divided by, and then Z squared equals little f 13 of x squared y. Right. So, you know, the picture's just the same as before. Here's my curve C. It's got 2G plus 2, which is 14 branch points. Right, and I've divided them up into 1 plus 13 others. Right, and that's how this ring is determined. And so now what is, so S, Ks restricted to C is P plus 2G12, and this is 5 times P. And so who is R of C and 5p. So, you know, I take this ring, so this is RC of P, 5. So, you know, the sort of geometry here is not unduly complicated. You'd think that the algebra would also be reasonable. But what's going to happen is that the algebra immediately goes into one of these codimension 4 9 by 16 resolution rings, and is really quite tricky. And to deform it is, you know, it's tricky and it's obstructed. Let me continue this calculation just for a minute, and then.
And in the case
2, 1, 2, 2. It's the same.
1 is not
2, 1 and 2, 2 are the same as far as this calculation is concerned, because I've taken a hyperplane section. When I get, the moduli space, you know, will, eventually the moduli space will look, the thing that Francesco is seeing, the moduli space looks like this. So if I take the 2, 2 guys, the guys where this quadric is like this, then they are allowed to deform away so that the point stops being a base point, exactly as in the PG equals 3, k squared equals 3 case I've been talking about. Right? So these guys here are allowed to go out into the world and become real quintic surfaces. Right? Whereas the ones over here, you know, you deform them as much as you like, and that base point stays a base point. And the quadric, which is P1 cross P1, of course, that's an open condition, so it stays a quadric. And so, you know, my whole point is to understand this phenomenon. And the phenomenon comes from this, from the different possibilities for writing down these codimension 4 rings. So look, maybe I can leave this as an exercise with the, so, you know, I'm going to have to write this out at the beginning of next time in any case. So, you know, this is sort of obviously generated by, if I'm just writing down monomials of degree 5, of degree divisible by 5, you know, I'd be better off, I'm sorry, I'm going to need this at the beginning of next time anyway. Let me just make the same change of coordinates I did before. This one is u, v, and w. Right, so I'm going to write down u to the 5th, u cubed v, u v squared, v to the 5th. And then I'm going to write down u squared w and v w. Right, so you know, these are of degree 5, then this one's of degree 10, and these two of degree 15. Right, and you can see that any monomial in these variables of degree divisible by 5, and not a multiple of z squared, can be written as a product of these guys, as a monomial in these guys. Right? And so here I've got x1. This is still a curve, x1, x2, x3. These are, you know, as far as the curve is concerned, I've got a plane conic. I've got a, this is, you know, this curve C is up here with a fixed point P on it. It's mapping to there. This is a plane conic. This is a double cover with 14 branch points, of which one is the marked point P. Right, and x1, x2, x3 are just coordinates in this plane. right? And then, so this one's called y, and he's of degree. So I'm going to think of these as degree 1, 1, 1, 2, and then Z1, Z2. So, you know, the strange thing about this number 13, the thing that makes him really, really awkward in our calculation here is he's not divisible by 5. So to get something divisible by 5, I have to multiply by u squared or by v. Right? And the relations So please do this calculation, then you understand next lecture very easily. So the relations are x1. So the relations, some of the relations are u squared to v is well defined. Right? So u squared to v is the ratio here, and it's also the ratio there. And you know, it's not directly the ratio there, but if I squared this guy, it would be the ratio. And then it's also the ratio there. So if I write down x1, x2, x2, x3, x3 squared y, and then z1, z2 in degrees 2, 3, 3, 4, 4, 5. Right, and then there are 3 more relations. Saying z1 squared equals something, z2 squared equals something, sorry, z1, z2 equals something, z2 squared equals something. And the thing I have to write down here is F13 u squared v times u to the 4th, and then u squared v F13, and then v squared F13. Where the square brackets means rendered. In other words, you know, for example, F13 may contain, for example, u to the 13th, right? And it may contain things like, I'm sorry, u to the 26th, right? It may contain u to the 24th times v, and so on, all the way down to v to the 13th. Yeah? So then, when I do u to the 4th times it, I'm getting u to the 4th times this, u to the 4th times this, u to the 4th times this, right? And then I say, well, these guys, this guy here is, this guy here is x1 to the power of 6. And then this one is x1 to the 5th, x2, and so on. And, you know, so there is a choice of rendering. So, I mean, this is just an observation. So look, if you want to understand the beginning of next lecture, please go through this calculation and make sure you understand it. And nothing very difficult here. So here, there's some game that I'm playing with monomials. I'm saying any monomials of degree divisible by 5 in these guys is a product of these guys, right? And the z squared is separate, right? And then, so if you take this expression, the F13 is a given thing, that's a curve on the, 13 points marked on the curve, right? But there's this strange game I'm playing with monomials here, which is I'm multiplying this by u to the 4th times F13. That makes a polynomial of degree 30 in u and v, right? And then I have to make a choice of rendering this into these monomials, right? And so I think it's clear that I've written down 9 equations. There are 6 equations here, and there are 3 equations here. And there are 16 syzygies holding between these equations. And so, you know, we're in this place in algebra which is basically quite complicated. If I want to deform this, earlier I had a ring which was a codimension 2 complete intersection. I told you several times, to deform that ring, I just change the terms appearing in the two codimension 2 equations. So here, if I want to change the 9 equations, I have to make sure that I keep the 16 syzygies, otherwise I don't get a flat deformation. And this is a very difficult algebraic problem. And so there are solutions to do this, which is taking these equations and trying to keep as much of this determinantal formalism as possible. Right? So when you write down these equations, notice I've got u to the 4th f13, you want u squared v f13, v squared f13. And you know, I can go from the terms in the rendering of this to terms in the rendering of this just by replacing terms from here by terms from here, terms in the first line by terms in the second line. So z1 squared here is quadratic in the top line, z1, z2 is bilinear in the top line and the bottom line, z2 squared is the bottom. Right? So the 2 different things we want to do with this, one is to put this in surfaces that are capable of deforming out to the type 1 surfaces. You know, and that's very strange. I've got this surface which has been pressed down to lie on a double quadric, and then I'm going to allow it to deform so that it's allowed to grow out to be a genuine quintic surface. And to do that, I've got to completely break up this determinantal form. And the other thing is I want to move it out so that it remains a double cover, but a double cover now of a non-singular quadric. And the non-singular quadric is this. Right? And so, for example, if I were to write here, you know, plus u naught, plus x naught, minus x naught, right, then the quadric has gone out to a quadric of rank 4. Right, I'll come back to this at the beginning of next time. Right? And so, you know, there's a dichotomy here. Either we completely lose the determinantal formalism, we do something that allows y, z1, z2 to be expressed as linear, so we allow y to appear in this equation of degree 2, we allow z1, z2 to appear in these 2 equations. Right? In that case, we completely lose the determinantal formalism. Right? Or we keep the determinantal formalism, and then we're allowed to mess around a bit. Right? And so that's the thing that leads to this picture. So, you know, this is still, you know, this is, Horikawa did this geometrically. His argument is based on analytic deformation methods. I mean, they're not really very different, but in any case, these methods are sort of basically at the boundary of current technology. And we understand a little bit more about these codimension 4 9 by 16 rings, but not much more, and they're still very hard to work with. Okay, yeah.
May I make a question?
Yeah.
I mean, of course, your knowledge about our knowledge about codimension 4 Gorenstein rings is just some kind of format, but we don't have any classifications.
Yes, but when we do deformation theory, we can do it. We can do deformation theory and see whether or not our deformations are compatible with the format.
This I understand.
Yeah.
The problem is your method cannot tell you that these are all possible deformation types.
They can.
They can?
Because they're first order deformation followed by second order deformation. So, you know, this equation, you know, sort of, there's something here like, you know, alpha times beta equals 0.
Yeah, this is the local structure.
Right. And the alpha is this thing, and the beta is the terms appearing here.
Yeah, I understand, but I wonder...
Look, imagine that you take this set of equations with this set of syzygies.
Yes.
And you make a first order deformation of them.
Yes.
right? Then I'm writing x1 plus some little multiple of x0, x2 plus some little multiple of x0, and so on. So everywhere in these equations, wherever there's a term, I'm allowed to multiply, put a little term in x0 in, right? And then I have to satisfy the syzygies, again modulo x0 squared, right? And so you get a problem which is purely linear algebra. This is calculating T1, right? And then maybe you find that actually by, you know, if the u0 here, if this little term at the front remains a quadratic of rank 3, then the whole thing can be pushed back into the determinant formalism. Right, this is a computational proof. Right? And then, you know, there is, at the end of the calculation, there is this obstruction. Right? And there's only one obstruction in the whole calculation. Look, you know, I mean, this is a long drawn out. Computer algebra now can now do this in a, you know, when I say, you know, almost automatic method.
My question is, imagine that you didn't know Horikawa work.
Yes.
And you are just making this computation. Could be sure that this gives you complete description of the modular space? Or
so look, one second. We're talking about the local deformation theory.
Local.
Yeah. And so in this case, the thing we're deforming is the curve.
You are deforming, yes.
So there's
we're
taking the curve and deforming in degree -1 is building the surface.
Okay.
Right. Taking the curve and deforming in degree 0 is varying the curve.
Okay.
Right? You know, so, you know, how do you prove that an intersection of varieties is non-empty? So, no. So the normal thing is we're in projective space. Projective space is proj of an affine variety. An affine variety is local at the origin, right? And then you're doing a calculation at the origin that says the intersection of the two ideals is not the origin. It's not only the origin, and that's the dimension calculation. That's where the thing happens. So you know, how do we know? You know, I mean. How do we know that there aren't many more components? Well, if, for example, PG equals 4k squared equals 8, then God alone knows. Maybe there are many more components. We just don't know. The analysis doesn't begin to work.
You cannot do the same analysis.
Well, you can try. You know, there's Ingrid and Roberto Pinatelli have a beginning of a paper, right? But they assume that the canonical map is composed of an involution or something. So, you know, it's, you know, you start off on a calculation which is supposed to be a nice, easy thing. You know, we know how to do PG equals 3k squared equals 2. Let's try the next case up, the next case up. And eventually we lose control. It's the same with, same with many things in life.